All right, welcome everybody. We'll get started here at the top of the hour. All right, and here we are. So, thank you everyone for attending our monthly webinar series here. The topic today is when DERs hit the feeder: voltage, backflow, protection, and fixes. Today we'll be presenting. We'll have a PDH availability for this presentation. If you check the chat, you will see the email. If you send a message to that email after the presentation is over, we will get with you and get you your PDH for the attendance here. So talking a little bit about our presenter today, I wanted to introduce and welcome Isaac Trueblood. He's been a power engineer at Commonwealth for about 8 years. He's a PE. He works out of our Spokane, Washington office. A lot of his experience in protection and control and system studies. So welcome, Isaac, and take it away.
Thank you, Ian. Yeah. At Commonwealth, we take safety seriously and like to start our meetings with a safety moment. Today's safety moment, I want to draw your attention to static electricity. I'm sure we have all experienced receiving a shock from static electricity. It is usually caused by gaining charge from fibers from materials rubbing together, socks and carpets. And that's mostly harmless, but in certain circumstances, static electricity can become dangerous. One such danger is that it is an ignition hazard. As such, remembering to take the time to discharge yourself before handling any flammable materials. This can be by touching a large piece of metal, preferably a grounded piece of metal. This will help prevent ignition of the flammable materials from the spark created by a static shock. I would just take a quick second look around you and think, what could you use to discharge yourself? I would point to any electrical appliances plugged in with a third prong, such as this guy here. That's showing up in that, but as the metal exteriors of those appliances should be grounded when they're plugged in, of course. An unplugged thing will not be grounded through that. I personally use my light switches. The screws on the cover plate are solidly grounded in my house, making an easy way to discharge myself just by tapping the back of my hand against the light switch. For most of us, the only time ignition due to static electricity can occur is when we're fueling cars at the gas pump. For that, there are rules and regulations that make ignition due to static electricity unlikely by dictating the design of gas station pumps and cars. However, an important concept to keep in mind is every safety measure is Swiss cheese. There are always holes, and the best way to prevent issues from slipping through those holes is to add multiple layers. So remember, after leaving your car at the gas station, make sure you discharge yourself, and then make sure that the metal gas pump nozzle touches the metal of the gas tank prior to pulling the trigger and filling up. That'll create everything at the same potential and prevent any sparks. It's also important to not get in and out of your car, as this can also cause an increase in static electricity buildup from you rubbing your clothes and your car seat. Back to our regularly scheduled broadcast. Dill, if you get this going, we got a quick questionnaire here. As you know me now, and I kind of want to take a mirror and get a quick gauge of the audience. What do you all believe are distributed energy resources? Select all apply. I have not told you anything yet, so there are no wrong answers. On my side. So our options here is A, battery, B, coal, C, hydroelectric, D, natural gas, E, wind, F, nuclear, G, oil, or H, solar. Let those.
So we have about 32 respondents. That's about half of the folks who are here today. So I think Here are the results. They're in the chat.
Yeah. So it looks like a lot of imbalances, a lot saying solar and battery. And unfortunately, it was kind of a trick question. They all are distributed energy resources. I may give points to anyone who left out nuclear, as those are relatively newer and rare. I myself have only recently heard about them. That being said, points don't matter. There will be no rating at the end of this presentation. The real point of that last question was to make you think and check any preconceived biases. When people talk about distributed energy resources, we often think of solar, wind, or batteries. However, any resource interconnected to the distribution system at voltages of around 100 kV or less that produces electricity is considered a distributed energy resource. I do concede my experience has primarily been with multi-megawatt solar, wind, and battery sites, as they are the majority of distributed energy resources that require consulting assistance over the past 8 years of my career. However, that was not always the case. There was a time before transformers where the voltages you generated at and the voltage you were plugging into were the same. So you would generate and use at the same voltage. We'll use 120 volts. Due to this, power was generated at low voltages that could only travel short distances before major power and voltages. This required generating resources to be closer to the load, generally within the same city block. One way to think about that is the power grid all started with distributed energy resources. After the invention and widespread adoption of transformers, power could be produced remotely and delivered to load centers. The economies of scale kicked in and generating sites consolidated into these larger and more remote sites. Distributed energy resources became more rare as it became less cost effective to run 10 megawatt sites than one 10 megawatt site. For the past 100 years, the electric grid has been expanding under this architecture. With a few exceptions, power flows from large remote generating sites through the transmission system down to the distribution system, then branching out to all of the individual loads. You can think of the power grid sort of as a river that is sending power downstream from generation up high to loads down low. However, those few exceptions are becoming less few every year as distributed energy resources are rapidly being adopted. Suddenly, the river is flowing backwards in places it hadn't before. This is causing friction with the historic systems that were not designed for generation at the distribution level. Traditional practices and legacy systems need to be examined and adjusted to account for it. Now, another quick question. How was the power grid changed by the adoption of transformers? This question, there is unfortunately only one right answer. A, decrease the amount of power that could be generated. B, increase the demand for distributed energy resources. C, decrease the load on the power grid. C, increase the distance between the load and the generation. Sip of my water as people are answering. Looks like we got about 40 or so responses in, and yeah, for the most part, people got that right. Answer is D. The adoption of transformers increased the distance between the load and the generation. So now let's talk about distributed energy resources and transmission connected generation. They share many of the same issues. However, the big difference is how they are connected. The transmission system has parallel branches, with many of them designed for power flow to flow in multiple directions. A generator increasing or decreasing output is an often hourly occurrence that changes the flow of power in the transmission system. Additionally, the high voltage nature of the transmission system allows for the whole system to be strong and electrically close. This allows for unexpected variations in the load and generation to be more evenly spread across multiple generators. There are always exceptions, but overall, the transmission system is resistant to many of the impacts of generation. I will stress it does not mean generation connected to the transmission system does not have these concerns, just that they are lessened due to the nature of the transmission system when compared to distributed energy resources. Some of the impacts of generation I will go over in this presentation will be voltage, power flow, reactive power, and short circuit. Another quick question, why are the impacts of generation greater for DERs? Again, only one answer for this one. Is it A, distribution systems are at lower voltages, making DERs electrically further away? Distribution systems are always designed for backflow conditions. C, distribution systems more easily spread sudden loading and generation changes over multiple generators. Or D, transmission systems can predict the future and are perfect. I honestly like D. Quick second to answer. Like we got some responses. Unfortunately, it seems like I may have misled a few of you with that bit trickier and double negative there. The correct answer is A, the impact of generations are greater for distributed energy resources because distribution systems are at lower voltages, making DERs electrically further away. I will say C, which more people seem to have, is the issue is that it's not spreading. It's not evenly spreading, I guess I should say. So might be a little bit trickier question, but as I said, points don't matter. So now I'll move on to impacts on voltage. I'm sure if anyone here works for or as a local utility, I'm sure you hear every light flicker or refrigerator malfunction the customers may blame on any change they can see. Everything from a changed fuse to a new substation. While some of these concerns may not be valid, distributed energy resources can cause unwanted voltage fluctuations and flickering. Having a source of generation that close to load means that generation increases and decreases can more easily cause voltage fluctuations that the system may not be capable of sensing or regulating. This can be especially true for customers near the end of the feeder. What can we do to mitigate this fluctuation? One way is to limit the time it takes for distributed energy resources to increase and decrease generation. It's also known as a generation's ramp rate. For predictable distributed energy resources like batteries or fossil fuels, this is often less a concern as ramp rates can be predicted and controlled. However, wind and solar, while often predictable, can on occasions be unpredictable. Sudden increase or decrease in sun or wind can make a site suddenly change how much power it can generate. A battery added to these systems can solve this problem. However, even a 5-minute battery, that is a battery that can produce 5 minutes of the total site's power, can make distributed energy resources non-financially viable. However, if you control the rate at which it increases its generation, it will greatly reduce the impact. This helps as customers will only experience a brief voltage decrease with the slow return to normal voltage rather than a sudden drop and rise. Additionally, it allows for voltage regulators to experience less wear from chasing sudden voltage increases and decreases. While ramp rates help with the flickering and equipment wear and tear, distributed energy resources can also cause voltage fluctuations a voltage regulator at a feeder cannot detect. One way to mitigate this is to provide communication between the voltage regulators and instrument transformers close to the end of the feeder, preferably near or at the distributed energy resource. This allows for a voltage regulator to determine when the DER is decreasing its generation and raise the voltage to prevent undervoltage conditions at the end of the feeder. Inversely, it can prevent the opposite case of voltage regulators creating overvoltage conditions at the end of the feeder caused by a distributed energy resources increasing generation. Lastly, a mitigation option, while effective, I will admit is less practical. By increasing the strength of a distribution system, the difference in voltages between the beginning and end of a feeder is greatly reduced, allowing for easier voltage sensing and regulation. However, this will require drastic measures, either increasing the distribution system's voltage or an increase to the power conductor sizing, neither of which is very practical or economical. However, I did want to include this option to cover that engineering wisdom of anything is possible. It will just cost a lot of money. So impacts on power flow. As we previously covered, historically, distribution systems flow in one direction, from their sources, often the transmission substation, to their loads. Distributed energy resources not only shift this paradigm, but do so dynamically. When a distributed energy resources generation exceeds the load, the feeder will cause a backflow condition. When a distributed energy resources generation exceeds the load on the feeder, it will cause a backflow condition that can cause damage to equipment or cause nuisance trips for protective equipment unprepared for a backflow condition. Additionally, this can flip the relationship between a transmission provider and a distribution owner from purely buying relationship to a buying and selling relationship. These relationships are based on contracts and agreements that can be difficult to untangle and renegotiate. There are a few ways to mitigate backflow conditions. The first is to simply limit the amount of distributed energy resource generation on that feeder. If the distributed energy resources never generate more power than the feeder load is requiring, there will not be a backflow condition. This is, however, trickier than it sounds, as loads are not static. The load on a feeder increases and decreases based on months, days, or even hours. Was Monday a holiday? I make Tuesday a greater load. However, there is a difference between a small few kilowatt distributed energy resource and a multi-megawatt distributed energy resource. There is a general rule that can be applied if the distributed energy resources capabilities are less than 20% of the feeder load, backflow conditions are considered unlikely. Now, I do want to stress that is not a hard rule, and any impact study should take more than just the 20% rule into account. You might be asking, so if we want to have distributed energy resources on our system, it can only be 20% of a single feeder. That seems pretty limiting. And you would be right, that is limiting. There are other mitigation options you can use. Depending on the distribution system's layout, additional loads can be relocated to that feeder. Alternatively, by upgrading the backflow capabilities of that single feeder, that the distributed energy resources generation is now applicable to all the feeders at that substation, expanding that 20% rule to apply for all the substation's feeder, not just the one feeder the distributed energy resource is on. Another mitigation option is to allow the distributed energy resources to curtail their generation under low load conditions. By installing instrument transformers on feeders that communicate with a distributed energy resource, it can sense the load and curtail its generation in real time to not exceed the load, preventing backflow conditions. This is often a large undertaking and is often non-financially viable, especially for independent distributed energy resource owners. But for a small utility looking to have some of its own generation, it can be a solution without the need for renegotiating those contracts or upgrading the system's feeders. Lastly, you can just do a backflow upgrade. As much as difficult, and often the best strategy will be to just renegotiate those contracts and upgrade those feeders for backflow conditions. In the long run, distributed energy resources have shown that they are increasing, and a backflow upgrade will likely be required in the future as distributed energy resources become more common. Take a quick sip. Another impact of power flow is on feeder ampacity. In addition to backflows, distributed energy resources will often tie into the systems using the existing line in feeders. This can cause issues with the amount of power the distributed energy resource generates exceeding the capabilities of the existing lines. Downstream of the distributed energy resource, also known as the load side, this will be a non-issue, as it doesn't increase the amount of power flowing to a load. However, if there is intended backflow, that the distributed energy resources generation minus that downstream load may still exceed a feeder's ampacity and the ampacity of the line and or equipment between the substation and that feeder. That substation feeder and that distributed energy resource. When I say the ampacity on the feeder, it means all parts of the feeder. This will generally require a review of everything on that feeder the distributed energy resource may exceed the ampacity of. This includes lines, switches, breakers, connection or jumper connections, fuses, relays, relay settings. It is a non-insignificant review. So, what are some ways to mitigate this? The first and easiest way is to limit the distributed energy resources nameplate. If you limit a distributed energy resources generation to within the allowable feeder ampacity, there will be less issues. But you want to stress, review of the feeder's ampacity between the distributed energy resource and the feeder is still needed to determine the limit before upgrades are required, or what upgrades are required if a specific nameplate is desired. However, such a review will ensure current equipment is capable of handling the power flow and prevent damage to the distribution system. This will also highlight the limiting factors on the feeder's ampacity, and sometimes an upgrade is a long time coming. Now, if you do want a distributed energy resource and someone is willing to foot the bill for an upgrade, it is the obvious way to mitigate this issue. However, a review of the feeder and potentially any other upstream feeders will be required. I've been on both sides, and often both parties are surprised that a $7 million upgrade is required. It's costly to increase a feeder's ampacity and can often make a distributed energy resource non-economical. But another wrinkle into this dilemma, multiple distributed energy resources can interconnect on the same feeder. Each distributed energy resource may individually not cause power flow concerns, but together can surpass the system's rating and or cause backflow conditions. Who pays for these upgrades and how they pay is always a bit of a tricky situation. There are multiple schemes that can be used, but ultimately it must be considered and thought out in advance for both the distribution owner who's going to require those payments and the distributed energy resources owner, because they will have to be the ones paying the bill for most of them, usually. So, next, I'll talk briefly about reactive power. This partially connects back into the impacts on voltage. Distributed energy resources need to be capable of maintaining acceptable voltage conditions for the distribution systems. This means providing or consuming reactive power to maintain acceptable voltages. Luckily, most rotating machines are capable of providing that reactive power without much concern. However, inverter-based distributed energy resources, which is what I have mostly experienced, need to have extra care put into their design to ensure they can produce these acceptable amounts of reactive power. A useful baseline, and is used in FERC Order 827, even though that is a transmission-based standard, it's still a useful baseline, is a requirement for inverters to dynamically produce power at a power factor between 0.95 lagging and 0.95 leading. To put it in simpler terms, an inverter-based resource, or any resource, that generates 100 megawatts of power at the point of interconnection is required to dynamically produce or consume 33 MVARs of reactive power at that point of interconnection. Each distributed energy resource will have specific standards that will be dependent on their distribution owner and their individual interconnection agreement with that distribution owner. So, what are mitigation options for achieving these MVARs? For some sites, reactive power compensation is the best solution. This usually involves adding capacitors or inductors, occasionally the type that switch on and off, and this will help to provide additional reactive power to the distribution system when needed, helping maintain voltages at the required levels. Another way to achieve reactive power requirements for inverter-based DERs specifically is to simply oversize them. A 100 megawatt site that only has 100 MVA worth of inverters will be unable to reach that reactive power requirement while maintaining the real power output. By oversizing the inverters, usually 20% is a good rule of thumb. 100 megawatt site with 120 MVA of inverters can provide the required MVARs without the need for adding capacitors or reactors. I do have to say, this is sort of the part where consulting engineers like Commonwealth usually step in, as deciding if oversizing your inverters or adding reactive power compensation like capacitors and inductors, switching or otherwise, is the best solution for any specific site. And this takes more than just rules of thumb and requires studies that take into account many other factors. Next thing I want to talk about is the impacts on short circuit current. Again, short circuit current, much like power flow, historically will decrease as the distance from the substation increases. With this architecture in mind, distribution systems are generally designed for protective equipment further from the feeder to draw on lower fault currents than protective equipment at the feeder. This keeps the protective equipment coordinated and prevents needlessly tripping power for branches without a fault. Such as if you have a line with a protective device in the middle, you'd rather that trip and take offline a portion of your distribution system than have the feeder trip offline and trip off the whole site. I want to stress this is not a wrong design. And for most feeders without distributed energy resources, it is still the correct design to have. However, distributed energy resources shift this historic architecture and cause increases in short circuit current that may exceed existing protective equipment ratings in the lines. Additionally, if not properly designed, a distributed energy resource can supply a fault that is otherwise isolated from the grid, creating unstable islands. As you can imagine, that specific scenario is incredibly dangerous. So, what do? How do we mitigate this? One way is for distributed energy resources to simply trip offline, like any other generation site, when a fault is detected or there are grid irregularities. This would prevent distributed energy resources from supplying faults with the increased fault current and prevent unstable microgrids. However, that is easier said than done. Major difference between a transmission interconnected generating site and a distributed energy resource is the system strength for a distribution system is much weaker, as we kind of talked about in our previous slide. This makes the difference between a load current and a fault current much lower. Transmission faults can be 10 times the load current. So you can have a load of 100 amps, and when it faults, it's 1,000 amps. Distribution system faults, especially near the end of feeders, can be as low as 2 times the load current. If you have 100 amps, it could be a 200 amp fault. The room for protection coordination and preventing these unnecessary power losses is much tighter fit for these distribution systems. This can especially be true with inverter-based resources, as they provide much lower short-circuit current than synchronous generation. However, tighter does not mean impossible, and with proper protective equipment and protective settings, distributed energy resources can be safely added to the distribution systems. This will still require an examination and possible upgrades or setting changes to existing feeder protection or protective equipment to ensure proper coordination and ratings. Fix it. And you might be asking, what about unstable islanding? That sounds pretty dangerous, right? And that is true. An unstable island is incredibly dangerous. However, this can also be mitigated. Having distributed energy resources and the protective equipment communicate with other feeder protective equipment. This will ensure the distributed energy resources protection knows when an upstream protection device is tripping offline, regardless of if the distributed energy resources protective equipment can detect the fault condition. This ensures that the distributed energy resources does not create an unstable island. There is, however, no free lunch. Communication over long distances costs money, and for proper protection communication, a stable, reliable, and fast connection is necessary. However, this is generally worth it, as unstable islanding is extremely dangerous. Going a little bit faster than I was originally anticipating, but that's all right. It means more time for questions. So now we're here at the conclusion. What can we take away from this presentation? Ultimately, distributed energy resources are a useful resource. They provide power closer to loads, reducing the inefficiencies in the power grid by reducing the amount of power losses and the transportation of power. With their widespread and increased adoption, distributed energy resources are a significant part of the grid. That being said, distributed energy resources can be complex and disruptive. What do we do about it? What's next? Well, that's simple. We keep moving forward. Also, the distribution is caused by the friction with historic decisions. Again, not bad decisions, just decisions made without the knowledge we have now. Now we know distributed energy resources are useful and increasing in number. Solar has been quite effective at being at loads. And going forward, unfortunately, this does mean going forward, we can't rely on historic processes and architecture. As this distributed energy resources penetration increases and the grid is expanding, we need to keep distributed energy resources in mind. And if we do that, the newer generation of distributed energy resources may be able to connect to existing lines without the need for multi-million-dollar upgrades. When comparing my last 8 years of experience against a century of the electric grid's history, it seems small. However, I have seen this change, even in that comparatively short time. Historical systems are evolving and being adjusted to accommodate for distributed energy resources. I will say, hopefully this presentation armed you with enough knowledge to be dangerous. In a good way. And with that, I thank you all for listening, and I'll open up for Q&A questions.
For anybody with questions, please post them in the chat or in the Q&A. Either one would be fine, and we will address them as they come in. So thank you for your presentation, Isaac. Very enlightening. We've seen a big explosion in the distributed energy resource field here. All sorts of things from residential solar to small community solar, microgrid projects, system reliability projects, things like that. So definitely an evolving space, and a space I expect a fair amount of growth here in the coming decades. So let's see here. I think there's some questions coming in.
Yeah, Ian, we
All
have
right.
one in the Q&A
Yep,
tab.
I see it.
Right.
Yep. So question coming in from Dennis. Are there specific design considerations or best practices to write into specifications for substation transformers that have historically seen normal power flows, but are now seeing bidirectional flows?
I would say it's not necessarily a specific design consideration that need to be put into specifications, as while distributed energy resources are increasing, it's these large increases that we're seeing where a feeder is now being offset, the load, the distributed energy resource is now exceeding that load. And while that is becoming more common, it is not something I would suggest we standardize for every feeder and substation transformer to be designed with that in mind. But that being said, if you anticipate it, it will make it less costly in the long run. Replacing a transformer is much more expensive than just building it with that in mind. Yeah, that is a good thing to consider, but I wouldn't suggest you having it be necessary for every substation transformer and especially every feeder on that substation.
Yeah, so I agree with you, Isaac. A couple more considerations too might be that Isaac's right. So if you're putting in DERs on a feeder, you're going to take load off transformers. If anything, you're helping the situation. Does it allow you to get a smaller transformer? But then you're more dependent on those DERs. So what if there's an outage or a condition where they aren't taking the load off? So I think we have to size for worst case conditions. On the flip side, if you have enough DER presence that maybe you can not only overcome the load, but even max out that transformer's capability for outputting power back to the grid, that could be a consideration. But I think in general, the system hasn't been sized for that. And if the next incremental DER that would come in that would cause that situation would then be responsible for that transformer upgrade, which may be a large cost and something that would stop that last incremental project. Unless we're really trying to be forward thinking about upgrades. The last consideration is when we're talking about bidirectional flows, that changes our protection quite a bit. So when we have source on our feeders, we should be thinking about that when it comes to relaying and protection. Are we able to sense that to make sure that our workers in the field are safe? And also the relaying packages around those transformers will have to evolve as well to be smarter relays to account for that bidirectional load and that source that might be on that feeder with the appropriate signaling to shut down any sources in the event of emergency.
I will also add a bit to that of just, I have seen multiple distribution owners who have rules about how much distributed energy resources can be on a feeder before things have to start being looked at and upgraded. And if you are that owner and you know, I'm going to put a distribution energy resource in 5-10 years that will likely exceed the load on this feeder and create backflows, having that in mind will save you money in the long run, especially when you design your protective equipment settings and making sure that protective equipment can be used in that way without nuisance tripping.
Sure, absolutely. Next question coming in from Christopher. Am I right in thinking that DERs are owned mostly by smaller utilities, co-ops, or municipals? If so, what design challenges do you think we will see as the DERs grow across the country in regards to standardization and implementation? In my experience, those types of IPPs are slow to adopt new standards and are often limited by funds necessarily to maintain and adopt new standards.
I would say I have not looked at statistics specifically about who owns all the distributed energy resources. I will say most of the time when I've been working and consulting on these, they have been individual owners. Like I said, I have also worked with utility owners looking to implement these distributed energy resources. And as they do become more common, the standardization implementation will need to be looked at. And you are right, often they will be slow because in these small utilities, I should be careful with wording there. They will often have a very select knowledge group, which will often be from years of experience. With the distributed energy resources being newer things, they often don't have this experience. But consulting firms like Commonwealth is kind of the solution to that. We don't have a standard for this. What do we do? And that's part of our job is to be, hey, you don't need to keep a distributed energy resource specialist on your payroll. We will help you determine and if distributed energy resources will be able to be adopted without issue. And I have worked to some degree in standardizations in the smaller utilities, which again is a service we can provide. They will be slow to adopt those standardizations, but as long as you can keep being bit by bit adding distributed energy resources as they come along, you won't feel too much of a pinch point until things will explode. But at the moment, things are still in a slower but steady increase.
Yeah, very good points, Isaac. Yeah, so when we're talking about the DERs coming online, a lot of these are connecting into existing IOU utility distribution grids. So it may be that the DER itself may not be as standardized because they'll try to, fit whatever makes sense for their business case. And it may be owned by an independent power producer or various owners. So, if you're talking about residential solar, it could be the customers themselves. However, we are seeing a fair amount of standardization across the industry by the IOU utilities or the traditional utilities. I should just say it that way, where they're going to have standards to interconnect. So there's going to be a process. There's going to be applications to be filed with certain permissions and requirements. There may be modeling requirements that are dictated as part of this, even at the distribution level, to make sure that these distribution resources are not going to interfere with normal operation of the grid, not cause any safety hazards, and not affect other customers on that line. So we are seeing that across the industry on the utility side is more rules and standardization of criteria to be able to interconnect. However, at the DER level, I think it still remains very much a use case argument that the DERs may not be as standardized just because there may be different use cases for those DERs. For example, some may be for stability, some are for reactive power, some are for energy arbitrage. There's all sorts of different cases, so you may build them differently based on that use case. All right. I don't have any other questions. I'll put in a last call for questions if anybody else has anything further. Again, thank you very much for your time in putting this together, Isaac. Much appreciated. Great job. And if anybody wants to be able to get a recording of this presentation, that'll be posted here after the presentation is over. If there's any follow-up questions or any questions that come up that maybe you think of after the presentation, feel free to reach out as well. And our experts will reach out and respond back to you on those questions as well. Thank you everyone for your time. Appreciate you attending our monthly webinar. Look for our next webinar series to be released for April timeframe, and we'll announce that there in March. So I look forward to seeing you guys again. Thank you very much, and we'll speak to you soon.